Welcome back, students. We have now finally got enough background that we can actually start applying quantum mechanics to systems. We'll start with a pretty simple system of particle motion. So we can think of this as translational energy. And we'll apply this to a kind of silly sounding scenario that is the particle in a box. We'll see at the end of today's lecture that this is actually relevant for discussing some real chemical systems. So like I said, we're going to be talking about the particle in the box today. We're going to be going a little bit out of order in the textbook. We'll start with the first part of chapter 15, and then we'll go over to chapter 16.3, which gives some real world examples of the particle in a box. The learning goals for today are going to be that we can state the wave function for a free particle, so a particle not in a box. And then we want to be able to do the same thing for a particle in a box. So we'll go over some detail about the particle in a box model. One of the key things we'll note today is boundary conditions. So we'll see what the boundary conditions do, and I'll spoil it a little bit for us, that the boundary conditions actually introduce the quantization into this quantum mechanical problem. So without the boundary conditions, we don't see quantization. And then at the end, we'll apply the particle in a box model to some real problems that we could encounter, some real scenarios. We'll do this in lab as well. And then lastly, we want to be able to solve some problems with the particle in a box. And so I'll leave most of the problem solving for in class, but I'll introduce that at the end. Okay, so to start, we want to think about the quantum mechanical free particle. And by free particle, what we mean is a particle that doesn't have any forces acting on it. It's just moving through space with nothing to interfere with it. To solve for the quantum mechanical free particle, we have to evaluate the Schrodinger equation. And again, we have to set it up in the way that makes sense to the problem. So let's go over and check this out. So here we see we have our Schrodinger equation, and what we have to do in order to solve for the motion of the free particle is adapt it to our problem. So there are two avenues that we want to address. First is the dimensions of the problem, and then second is the potential energy. So starting with the dimensions, we're going to limit our first discussion of this to one dimension. We'll see that if we want to extend it to 3 dimensions, it's actually pretty easy to do, and we'll save that for next lecture. But today we'll leave this, and we'll just have a function of x, and that's going to be totally okay for us. The next thing we want to do is look at the potential. And remember, what we're talking about here is a free particle with no forces acting on it. So what that means is that it doesn't have any changes in potential energy. The potential energy is constant throughout the whole scenario. And remember, let me actually turn my camera on for a second here. So remember what is happening with energy. In chemistry, we don't really talk about absolute energy. We talk about changes in energy. So for example, I can take this pen and I can be moving it around here, and I can ask you what the energy affecting this pen is. And you have no idea. You don't know if I'm holding it over the ground, the table, my lap. You have no idea how much this can fall. You don't know its potential energy. But what you do know is that the potential energy isn't changing as a function of it moving. So there's whatever the potential energy is, doesn't really matter because it's not changing as I move this pen. And that's going to be important for us. So if we have a situation where the potential energy is constant, it doesn't matter what it is. And what we can do then is set the potential energy equal to 0 for the free particle. So that's going to remove this whole term for us. And when we do this, we have a differential equation that we can actually solve pretty easily. So I'm going to group all the constants on one side of the equation because that's a little bit easier to look at. And I'll end up with the following. The second derivative of our wave function with respect to x has to equal negative 2me over h bar squared times the wave function. And that's it. So with this differential equation, we can actually solve this. This will be the only differential equation that we're actually capable of solving in this class. We'll just be provided with the rest of the answers. But here, we need to take 2 derivatives of our function and return that function multiplied by a negative constant. And we've talked about this in class, and you're probably aware that the answer is going to have something to do with cosine of x. It turns out that it's going to be easier for us if we treat it as imaginary numbers. And so what we're going to do is simplify this again. We're going to group all of these constants together and say that this needs to equal negative k squared psi of x. So again, we're saying that k squared is equal to 2me over h bar squared. And then we can set this in and say, well, the solution to this equation is equal to e to the kx, or e to the ikx, rather. And if we were to take a derivative of this, right, one derivative would give us ik e to the ikx, and then a second derivative would give us negative k squared e to the ikx, which is exactly what we need to see. Now, before we get too far into this, I want to point out that there is another valid solution. And that other valid solution is, of course, e to the minus ikx. If we were to take two derivatives of this, we'd also return negative kx squared, or k squared e to the ikx. Or yeah. And so what these two wave functions amount to is motion in the forward direction and motion in the reverse direction. And that, I think, it makes some sense to us. Now, the other thing I want to point out is this k here. We've defined k up there as k squared equals 2me over h bar squared. But this k is actually our same wave vector that we described before. So back when we talked about waves, we defined k as 2 pi over lambda. That was our definition of k. And we just used that so we could do things like write the wave as a sine kx minus omega t, right? We had these definitions. So with this, we can actually show that this is the same k. So first, we'll use the de Broglie wavelength and say that the wavelength is equal to h over the momentum. And that gives us 2 pi p over h. Now, h over 2 pi is h bars. This is equal to the momentum over h bar. And then you may remember from the Schrodinger equation that the square root of the momentum is 2m times the energy. So that means one momentum is simply equal to the square root of 2m e over h bar. And then we could write this as the square root of 2me over h bar squared. So here you can see that this wave vector, 2 pi over lambda, gives us the same definition as we just plugged in for k here. Other really important things to note is that in this case, right, k is equal to 2me over h bar squared. So m is a constant, h bar is a constant, e is the energy that has no restrictions on what the energy can be. So there is no quantization here for our function. It could have any k, it could have any energy. The free particle, when described using quantum mechanics, doesn't actually introduce any quantization conditions. The last thing we can do is solve for the eigenvalues. And the eigenvalue is simply going to be what happens when we plug in this energy to the equation. So what we need to do is take negative h bar squared over 2m, take two derivatives of our wave function with respect to x, and then whatever that returns multiplied by our function, right? Now those are the eigenvalues. In this case, those are the energy. And we can simply get that. We already kind of know what we expect by rearranging this equation here. So our eigenvalues, our energies, are going to be equal to h bar squared k squared over 2m. And if we went back in, plugged either one of these equations into our differential equation here, this is what we would return for our energy. And again, no quantization here. So the next thing we want to do is try to figure out where the particle is. Can we locate the free particle? And to do that, we need to use our first postulate. So our first postulate states that the probability of finding our particle within some region dx is equal to the following. So we need to take our wave function, so I'll use the forward wave function, and take the complex conjugate of that and multiply it against our regular wave function with respect to dx, and then we need to normalize it. So I said before that in most cases our wave functions will be normalized. This one is not yet normalized. And so to normalize it, we need to integrate over the wave function here. So we can go ahead and set this up and do this integration. Now, what we'll note is that we have a sine function. And if I asked you to find the area of the curve under the sine function, you would say, well, the sine function goes off into infinity, so we really can't solve it. And that's true. So what we're going to do is use some arbitrary distances. So we're going to say we're limited from L to minus L. We have some big space that we're searching over. And again, if we're not integrating from negative infinity to positive infinity, we actually have some finite area that a sine curve can be. So that's okay. Now this integral on the bottom, let's go ahead and plug in values here. And so what we'll get is e to the minus ikx, because we're taking the complex conjugate, and then e to the ikx dx over the integral from negative L to L of e to the minus ikx e to the ikx dx. Now, what this gives is, of course, on top, we just have dx. And then on the bottom, we have the integral from negative L to L dx. That's what happens when you multiply these two terms together. Now, when we do this, okay, we can evaluate that integral of dx, and essentially we get, L minus L, or 2L. So this gives us the probability density of finding our particle anywhere. We could solve it if we wanted to. We could say, where's the chance of being within a certain region? But we don't need to do that. We can just look at the equation. And this says that the probability of finding our particle within an interval dx is dx divided by 2L. And if our space we're looking in goes from negative L to L, 2L is the whole space. So what this expression tells us is that we have an equal chance of finding our particle anywhere in the interval. And that makes sense. If we have a particle randomly moving throughout some space, we would expect it to be evenly distributed over the whole space. So again, good and making sense. Now, we'll move from here to a particle in a box, and we'll see that what we observe, namely that we have a continuous energy and an even probability distribution, changes once we restrict the particle in the box. And that's because the wave nature becomes more apparent when we restrict it into a box that has the same size as its wave nature. So let's go back to the slides here. We'll go back to the iPad and do some more math in a second. We're going to look here at a particle in a box, and I have an image over here of what a particle in a box is. We're restricting the particle to a certain region of space. We're saying that box goes from x equals 0 to a. The dimensions here aren't important, but we choose 0 to a because that helps the math. So we'll see when we change to a particle in a finite depth box, we change the coordinates there again to make the math simpler for us. So how do we restrict a particle in a box? Well, we say inside this box, the potential is 0. The particle can move freely inside the box. It's in the box. Outside the box, we have a potential that's equal to infinity. So the particle can't exist if it has an infinite potential. And so it can't exist outside of there. So it's restricted to the box in this way. Now, what we want to do is try to figure out, how do we go about solving this problem? And the way we do it is, of course, solving the Schrodinger equation. And it turns out we can solve this Schrodinger equation as well. It's a bit more complicated because our potential isn't simply equal to 0. We have 3 regions, 2 of which are kind of the same, where the potential is equal to infinity. And so we had to solve the Schrodinger equation twice. So the first way to solve the Schrodinger equation is going to be exactly the same. So let's go back to the iPad here. Inside the box, our potential is still 0. So that's going to give us the same equation to solve that we did last time. I'll go ahead and write that out. Essentially, we have again, two integrals of our wave function with respect to x is equal to negative 2me over h bar squared times psi of x. And this will have the same solution that it does before. We'll see, though, that it actually makes it easier, again, to use the cosine and sine functions, the trig functions, as a solution to this. So last time we used e to the ix because our particle was free. Here we want to say, okay, this time we're going to use a different function, and we'll use it in terms of sine and cosine. So we'll have a sine kx, and then plus b cosine kx. And if we took two derivatives of this function, we would see the same, we would get the same answer. Again, we are using the same definition here of k as we had before. Now, outside the box, our potential isn't zero, right? Our potential outside the box is now infinity. So how does that affect our problem? Well, let's go ahead and check it out. So we would have negative h bar squared over 2m times two derivatives of the wave function with respect to x plus infinity times the wave function equals e times the wave function. So we can do some rearranging here, and it will come up with the following. So we would get that two derivatives of our wave function with respect to x is equal to 2m over h bar squared infinity minus e times the wave function. So I subtracted the infinity psi of x over, factored that out, and then I switched the order by using the negative sign here. And in this case, what is this? Well, if we have a finite constant multiplied by infinity minus another finite number, we end up with infinity. Hopefully you remember from the first postulate that this is going to be a problem for us. So if we have two derivatives and we're equaling an infinite number, that doesn't end up working. So this gives us a second derivative that is not existing and isn't well defined. And so that means that we can't have this wave function. Our wave function can't be a finite number. And the only solution then that makes any sense is if the wave function is 0. And that makes sense to us because what we were trying to do is restrict the particle to a box. And so we have successfully restricted the particle to a box. It exists inside the box, it has a wave function. Outside the box, it does not have a wave function. So what we need to do next is apply the boundary conditions. And remember, I said the boundary conditions are going to be important. So the boundary conditions are going to give rise to our quantization, and what are they? Again, using our first postulate, our wave function must be well-defined and single-valued. So since it must be single-valued, that means at these points, so let me draw this box here. At the box edges, at 0 and a, our wave function needs to be 0 because outside of the box, the wave function is 0. So that means at those points inside the box, it also must be 0. Inside the box, it can do anything it wants as long as it's 0 on the outside. Of course, now that's not single valued. So let me draw a more real one. It can do anything it wants inside the box as long as it's 0 outside the box. So that's the quantization conditions we're going to apply. Namely, we're going to apply that the value of the wave function at 0 and the value of the wave function at a must be 0 in order to have a continuous function. And we can go ahead and solve for that. So we'll go ahead and just plug these numbers in and see what we get. So the first thing we'll do is we'll take our wave function again, which is up here. So our wave function is psi of x equals a sine kx plus b cosine kx. And we plug in 0. So psi of 0 gives us a sine of 0 plus b cosine of 0. And it must equal 0. So sine of 0 itself equals 0, and cosine of 0 equals 1. So what that gives us then is that b equals 0. Since the cosine term equals 1 at 0, we can't have any contribution from cosine into a wave function, or we'll violate the conditions. Next, we'll do the same thing for a. So we'll do psi of a. And here we'll have a sine ka equals 0. We don't have a b cosine ka because we already know that b is equal to 0. And what this gives us then is we need some term where sine ka equals 0. We could also have a equal to 0, but then we would have no particle in the box. So that's not interesting. So when does sine of ka equal 0? Well, sine of ka equals 0 when ka equals n pi. And this gives us a condition here that shows us that k is equal to n pi over a. So we can plug this back into our equation and see that our wave function that was equal to oops, let me get the a in there. That's equal to a, which is our normalization constant, sine kx plus b, which was 0 cosine x, is actually, we can write that as capital A sine n pi x over a. And this is our solution to the wave function. So what we can see is that our boundary condition inserted quantization. And what's the quantization? Well, we have to exist in integer or half integer numbers of wavelengths. So one way we could start and end at 0 is if we had one wavelength in the box. Another way we could do it at 0 is if we went up and down and we had one full wavelength. We could have 1.5 wavelengths, we could have 2 wavelengths, and so forth. But these are the only conditions that will actually be 0 at the edge of the box. To fully solve the wave function, we're going to need to normalize this. I'm not going to go over how to normalize it. That's going to be the homework problem for today's class. But I'll go through, kind of the strategy for it so you can be set up to do well. So the condition for normalization, recall, is that the integral over the space that matters to us, which in this case is 0 to a, of the complex conjugate of our wave function multiplied by itself equals 1. So in this case, what we'll need to do is we'll need to integrate the square of our wave function. So I'll write a sine n pi x over a squared, and integrate this and assure that it equals to 1. And what we get at the end of the day will be our normalization constant a when we solve this equation. Don't worry too much about the sine squared n pi x. That should be in your equation sheet. If it's not, just Google search it. I think, actually, you know what? I think it's in the book, but not in the equation sheet. So you can check your book for it, or you can Google search how do you solve the sine squared integral. I don't want you to stress too much about that. It's using some weird trig identity. And this gives us a normalization condition for our constant a. Then what we can do is, of course, plug it back into the Schrodinger equation. So if we plug our equation here, a sine n pi x over a, and I'll give you the answer. So the wave function is actually the square root of 2 over a sine n pi x over a. And if we plug this back into the Schrodinger equation, so scroll up here, we plug this in and solve for the energy, we can figure out what the energy levels for the particle in the box are. And that'll be on the homework as well. So just by taking 2 derivatives of this, multiplying it by h bar squared over 2m, we end up with the following: that the energy levels are now quantized, or dependent on this quantization condition coming from the boundary conditions, the number n, and they are equal to h squared n squared over 8ma squared. All right, so back to the slides, and we can see all the information that we just covered on the board. What we want to do now is actually evaluate what these equations look like and how we can think about them. And to do that, what we're going to do is plot them in this kind of box. So we have the wave functions. You can see we have 1 half wavelength, 1 full wavelength, 1.5, 2 wavelengths, and so forth. We can go on if we want. But we don't center them all around 0 because we recognize that they have some energy associated with them. So our first eigenfunction here is down at the bottom with an energy equal to h squared over 8ma squared, because the energy is equal to h squared n squared times 8ma squared. And the second function is up here at 4 units of energy, because we have 2 squared is 4, then we have 9 units of energy, 16 units of energy, and so forth. So this is a plot of the wave functions. Now, what we might want to do is figure out, okay, well, where is my particle in the box? And this is where it gets weird. So remember, and we'll go through this in class in more detail, but to figure out where a particle in the box is, we evaluate our expression. And we use our first postulate of quantum mechanics, and we can evaluate that. And you'll have some practice doing that. But we can also just look at this graphically. It's going to be the same kind of thing. So what we want to do is square these functions, and then that's what kind of give us an estimate, right? The area under the curve of that is where the probability of finding the particle is. So if we square that, we see some weird stuff. We see that a particle in this first quantum mechanical state here is much more likely to be in the middle of the box than at the edge of the box. We see a particle in the second state is more likely to be at 3/4 of the way through or 1/4 of the way through, not very likely to be in the middle and not very likely to be at the edges, and so on. We see this weird trend. So since our particles are waves and we're confining them into some space that's similar in order to the magnitude of their wavelength, we don't see even probability distributions. We in fact see an uneven probability distribution. So our particle is not likely to be anywhere in the box. It's biased towards different spots. And we can mathematically solve for this. It's pretty straightforward, and I'm happy to go through some examples of that in class if we want. Another strange thing that comes out of this is we have this 0-point energy. So our particle confined to a box has to have some energy. And that's because there's no way to have less wavelengths than this and still hit 0 at both edges. So our quantization, our boundary conditions give rise to this weird phenomenon called 0-point energy, where our particles have to have energy. And this is going to be true for things like molecular vibrations, and we'll see that here in a couple lectures. A less obvious result, and I'll go through this as well, is that in the limit of high energy, this quantization gives rise to a continuous energy spectrum. And you might look at this and say, oh, hold on, that doesn't make any sense at all. That's not possible. We're at 1, 4, 9, 16. I can do math here. I know that as we go higher and higher and higher, this is going to be blown out, and I'm going to get so far away, and I'm going to get big, huge quantizations in the real limit of of high energy that we would find a real particle in. And we can evaluate that using a little bit of a trick here. And what we do is we actually need to compare the energy that a particle has or the energy difference, rather, between two states to the total energy that the particle has. And we'll see that that actually becomes continuous as we get to higher and higher energies. So what do I mean by that? What am I talking about? Let's go ahead and look at this. So to determine if something is continuous, what we can do is say, well, how does the change in energy, like I mentioned, how does that compare to the actual energy that we're at? So, for example, when we start at 1 and go to 4, we've now increased 3 units of energy. But what happens if we, are at higher energy levels? And so to do that, we can go to the following. So our delta E here is going to be E n plus 1 minus the current energy. And then we'll compare that to the current energy and see how going up 1 step compares to the step we're at. For this, we'll simply plug in the value. So for our numerator, I'm going to write it like this. We'll have h squared, and then I'll have the n. So I'll have n plus 1 squared minus n squared over 8ma squared. And that's a simplification of just plugging in the 2 values for our e's. And on the bottom, we have h squared n squared over 8ma squared. So when I write it like this, it's pretty obvious that our h's and our 8ma's are going to go away. They're there every time. And that gives us n plus 1 squared minus n squared over n squared, which we can simplify to 2n plus 1 over n squared. So this, again, tells us that the difference between our energy levels does increase by linearly, by n. But the actual energy levels increase quadratically by n squared. So again, what does this mean? We'll look at what happens when we go from n to n plus 1. So we'll start by saying what happens when we go from 1 to 2. And then we'll look at our ratio. So here, I'll calculate delta E in terms of h squared over 8ma squared. And of course, this is 3. I'm going up from 1 to 4. So that seems maybe pretty big. And then our delta E compared to E, again, solving this equation here, we get 3 as well. So we're taking a pretty big step as you go from 1 to 2. What happens if we go to 10 to 11? Well, here, 10 squared is 100, 11 squared is 121. So our delta E is 21. Our delta E is increasing, right? But going from 100 to 121 is a lot smaller of an ask than going from 1 to 3. So if we take 21 and divide that by the energy we started at, 100, we end up with 0.21. And we could do the same thing here. We could go and say, okay, well, as we go from what about 101 to 100 or 100 to 101. I wrote that wrong. So if we go from 100 to 101, what does that get us? Well, here we're going to 201. So again, our spaces are getting further apart like we anticipate. But what we have is now 201 divided by 100 squared, which is 10,000. And that is 0.0201. So even though our energy levels are getting further apart, they're not so far apart compared to the last one. And again, it's much easier for a particle to get 200 units of energy if it's already sitting at 10,000 units of energy, if that makes sense, than it is for a particle to, say, get 5 more to go from 4 to 9. We'll go over in class in more detail to make sure we understand how we can show that the particle in the box does in fact become continuous in what we would expect classically as we go into the high energy limit. So we'll look at that again in a little bit more detail. Before we finish, I want to try to apply the particle in the box model to real systems. So we have this model that's very simple of confining an electron into a box, or a particle rather into a box, but we can actually use it to get some pretty decent information. So we can treat conjugated pi systems as if they are boxes. And this is what we'll do in our second lab. So we have butadiene, hexatriene, and octatetraene, and they're both diphenyls. The diphenyls help make the model work. And we can take these and treat these as if they are boxes. And we can treat the electrons as if they're in energy levels. And you hopefully remember something like this from organic chemistry, that when we have these aromatic systems, each of these MOs, right, we can treat these as MOs, and we'll talk about MOs in more detail at the end of class. But the lowest energy has 2 electrons and 2 electrons, and then we have the HOMO that has the final 2 electrons. So this is an example for hexatriene. And if we were to excite this, we would be moving 1 electron from the HOMO to the LUMO. In this case, for hexatriene, that would be n equals 1, 2, 3 to n equals 4. And that we can use that. We have this delta E, the energy that excites this transition, and we can use that to solve for the box length, or the length of our conjugated system. Again, we'll do this in more detail in lab, and I'll go over this in class if we want. But what we can see is that we get pretty reasonable predictions for treating this system as a particle in a box. So we get the same kind of trends from calculations that we would if we would actually go through and measure the length of these bonds. So again, pretty remarkable that we can get these measurements just by pretending that it's a one-dimensional box that we're restricting our electrons to. In the next few classes, we're going to extend this particle in a box model to more real systems. And we're going to rely on this model to compare more complicated systems as they develop. So it will be helpful for you to familiarize yourselves with it now. And with that, I will let you go, and I'll look forward to talking about this more with you in class.